Let's consider a case of a circular uniform motion. So let's analyze the title. Motion. We're moving. Circular in a circle. Uniform. Uniformly. Which means at the same speed. Uni means doesn't change. Same. So what does that mean? It means that we're turning in circle. And we are doing in such a way that our velocity doesn't change. Uniform. So uniform refers to the velocity. So this is an interesting case because it refers to the fact and echo the ideas or the idea of the acceleration. Remember, the acceleration is present or non-zero whenever the velocity is altered or whenever there's a change of velocity. But remember that the velocity is a vector which has two components, magnitude and direction, which means that if there is a change of velocity, there is an acceleration, and this acceleration can change either the magnitude or it could change the direction. Either way, or both. We know the first case. We've seen it in the one-dimensional case where you travel at constant velocity, an acceleration pops up, and if the acceleration is positive, your velocity is going to increase in magnitude. If the acceleration is negative, then the velocity will decrease in magnitude. This uniform circular motion or circular uniform motion is the case where the acceleration actually changes the direction and not the magnitude. Not the magnitude because we're dealing with uniform. Therefore, the speed is going to be invariant. So let's do a bigger picture. So at this point, remember the velocity is always tangential to the trajectory. Therefore, the velocity is up, and its magnitude is given. So let's say whatever, 2 meters per second. At another time in or another position of time, the velocity, the particle is right here. Therefore, the velocity is again still tangential to the path, and again its magnitude better be the same. At some other time, velocity is still perpendicular, I'm sorry, tangential to the trajectory with the exact same magnitude, and so on and so forth. So the fact that the speed is invariant refers to the fact that we're dealing with a uniform motion, and circular means we're turning in circle. So if the magnitude is not altered, it means that there cannot be an acceleration present in the same direction as the velocity. There's no way, because if there was such an acceleration, the magnitude of the velocity will change. So if the magnitude of the velocity doesn't change, there cannot be any acceleration parallel to the velocity at all times. But obviously, this direction is different from this direction, which is again different from this one and different from this one. So there's going to be something that changes direction. And that cannot be in the same direction as the velocity at all times. Well, the answer is that's the guy. The acceleration is perpendicular to the velocity at all times. And this is the one that will cause the direction of the velocity to change. But since it's perpendicular, it will not affect its magnitude. Remember, the same as projectile motion, the acceleration was always going down, down, down. The velocity vector in the x direction was always horizontal, 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 since a, which was minus gj, was perpendicular to vxi. Vx was unaltered, and vx was a constant for the whole path. Same thing here. A is perpendicular to the velocity at all time, therefore the magnitude doesn't change, but the direction will. So that's what we call circular uniform motion. Now we could derive the same way as we had A is equal to g, 9.81 meters per second for the case of projectile or free falling in the negative direction. We could derive the functional form of the magnitude of the acceleration for the case of a circular uniform motion. But for us to be able to do so, we would need to change the coordinate system. In this class, we'll be dealing with the Cartesian coordinate system. If we were to change our perspective and introduce a new set of coordinate system, which is, for instance, tangential and normal, so a new set of coordinate system that follows the particle, we would be able to derive the functional form of A, uh, which I'm not going to do. But you will see it most likely in higher level physics class, theoretical mechanics, and or you should be able to see it in a dynamics class in mechanical or civil engineering. So let's accept the definition. Actually, it's rho. Rho for instantaneous, R for circular. So if you're turning in circle, the distance between the particle and the center is always the same, R, so this will be a constant. So that's the definition or the functional form for the magnitude of the acceleration as you're turning in circle with a constant speed. So every time you're dealing with a circular and uniform motion, you know that you can use this formula to estimate, to calculate the magnitude of the acceleration. The direction, you know it. It's always directed towards the center, always perpendicular to the velocity, which itself is always only tangential to the path. So, that is nice. What does that tell us? It tells us that if v is a constant, which we knew because we called it uniform motion. Oh, again, there. If r is constant, then a is constant. Similarly, as you decide to turn with a bigger speed, you're going to increase the velocity. If you do this and keeping your distance with respect to the center of rotation constant, then the acceleration will increase. And it will increase much more because of that little power of 2. Similarly, if you move away from the center of rotation and you start traveling in a bigger circle, so r is bigger, the acceleration will get smaller. This particular acceleration has a name. It's sometimes called centripetal. Centripetal acceleration. It has a cousin which is called centrifugal. Centrifugal, which comes from a force which is called centrifugal force, which it's kind of a bogus force because it's a kinematic force, which means that this force only shows up depending on which type of coordinate system you pick. If you're in Cartesian or even tangential and normal, you will never see that centrifugal force pop up, and therefore you will never see that associated acceleration. For you to reveal it, you need to go into polar coordinate, which is E theta, E n, E r. But the difference between polar and tangential and normal is that tangential and normal is a coordinate system that moves with a particle, while polar is fixed. It's like the Cartesian. So if there is a rotation involved, the coordinate system that you consider is rotating with respect to the dynamics or the kinematics of that rigid body of that particle, which creates that force. So that's why they call it a kinetic force, because it's not really real. It only pops up if you use that particular type of coordinate system, or if you are looking at this process or this dynamics from a coordinate system which is rotating with respect to that system. Anyway, so let's look at this guy, V. So as far as we're concerned, this is our centripetal acceleration, which is the one directed towards the center. Now, velocity, remember, is distance versus time, or over time, sorry. Now, if you turn in a circle, uh, one revolution is the circumference of that circle, which is nothing else than 2 pi r, right? And the time it takes to go one revolution is usually called a period, which I will write big T. So let's try to replace this into our formula and express the acceleration not in terms of the velocity, but rather in terms of the period. We had a v squared, So yeah, v squared. So we're gonna have to square this. 4 pi squared r squared t squared, and then we divide this by r again. Up. We can simplify one of those r, and therefore we can rewrite the acceleration as this. Same thing, except this one is expressed as a function of v, while this one is expressed as a function of time. So what does it tell us? It tells us something weird. Oh no, okay, yeah, that is good. That is good. So either you use this functional form if you're given something about the velocity of the object going in a circular uniform motion. If you're being given something or some information about the time it takes to rotate, like a planet or a satellite, then you might rather use this formula. Either way, they should be equivalent.